This diagram illustrates the key components of the Tessent On-Chip Clock Controller, on-chip clock, used in scan testing. The system begins with a scan-in signal that enters the clock control block, which manages clock distribution during test modes. The clock selection module receives 3 input clocks, clock 1, clock 2, and clock 3, and selects one based on test requirements. This selected clock is then routed to the clock control block, which synchronizes it with scan operations. The clock control block outputs an enable signal to the clock gating module. This gating function enables or disables the clock path to the core logic, ensuring power efficiency and timing control during scan tests. Finally, the processed clock exits via clock out, ready for use in the test sequence. This diagram illustrates the clock control architecture of the Tessent On-Chip Clock Controller, OCC. The OCC manages clock distribution to core flops during both functional and test modes. In functional mode, the reference clock feeds a PLL to generate a fast clock, which is then routed through the OCC to drive the design. During test mode, the OCC switches between different clock sources. The fast clock is used for at speed capture, while a separate slow clock drives shift operations and slow capture. The test mode signal controls this switching behavior, enabling precise timing control for scan testing. The OCC ensures that the fast clock path remains shared between functional and test modes, simplifying clock tree synthesis and improving timing closure. Additionally, the reference clock is typically a free-running pulse, always signal, ensuring stable operation of the PLL. This diagram illustrates the on-chip clock controller, on-chip clock, in shift mode, where scan enable is asserted to enable scan chain operation. The slow clock is used for shifting data through the scan chains, including the shift register and sync cell blocks. The scan-in signal enters the shift register, and scan-out is generated based on the current state of the register. In shift mode, the on-chip clock controls clock gating via fast clock gating control and slow clock gating control. When scan enable is high, the slow clock path is activated for shift operations, while the fast clock remains gated unless needed. The bypass path allows direct routing of scan data when required. The test mode signal determines whether the on-chip clock is active. In shift-only mode, test mode is low, but shift operations still use the slow clock. This ensures consistent timing across modes. The on-chip clock control block manages output signals like scan-out register and bypass clock, coordinating with the shift register and clock control logic. This diagram illustrates the shift mode operation of the Tessent On-Chip Clock Controller, on-chip clock. When scan enable is asserted, the on-chip clock enables the slow clock path to drive the scan chains. The synchronized cell synchronizes the scan-in signal, and the shift register captures control bits for clock gating logic. The shift register clock gating control controls the clock gating for the shift register, ensuring that only the slow clock is used during shift operations. This maintains consistent timing across both internal and external test modes. The bypass shift flip-flop register allows bypassing of certain flip-flops during scan, improving test efficiency. In shift-only mode, test mode is deasserted, disabling on-chip clock functionality while still enabling scan shifting via the slow clock. The fast clock gating control and slow clock gating control are controlled by the clock multiplexer select signal, which routes either fast or slow clock based on capture mode and other test conditions. The final clock out is selected accordingly. This diagram illustrates the Tessent On-Chip Clock Controller, on-chip clock, configuration during slow capture mode. The reference clock feeds into a PLL, which generates multiple functional clock signals, functional clock 1, functional clock 2, and functional clock 3. These clocks are routed to 3 standard on-chip clock instances, enabling synchronized functional operation. In slow capture mode, the slow clock is used for capturing data into scan cells and shifting condition bits in the shift register. This clock path bypasses the PLL and directly connects to the on-chip clocks, ensuring low-frequency capture operations. The test clock is also shown as an independent path, allowing test patterns to be shifted using either the test clock or functional clocks, depending on the shift-only mode setting. One on-chip clock is marked as inactive, indicating it's not participating in the current test phase. This diagram illustrates the Tessent On-Chip Clock Controller, on-chip clock, operation during slow capture mode, where fast capture mode is set to 0. In this mode, the slow clock is used for both capturing data into scan cells and shifting condition bits in the shift register. The scan-in signal enters through the sync cell, which synchronizes it with the test clock domain. The shift register clock gating control block controls the clock gating of the shift register based on the current state of the scan chain. When scan enable is active and capture cycle width 1 to 0 specifies a capture cycle, the on-chip clock routes the slow clock to the scan cells via the clock out path. The bypass shift flip-flop register allows bypassing of certain flip-flops during scan operations. The on-chip clock control logic manages the selection between fast and slow clocks using multiplexers controlled by fast capture mode and shift-only mode. In slow capture mode, the slow clock gating control enables the slow clock path while disabling the fast clock path. The final clock out signal drives the scan chain, ensuring proper timing for capture and shift phases. This diagram illustrates the fast capture mode operation of the Tessent On-Chip Clock Controller, OCC. When fast capture mode is asserted, the fast clock is used to capture data into scan cells and shift condition bits in the shift reg. The sync cell synchronizes control signals, while the shift reg CGC enables clock gating for the shift register. The scan-in signal controls the scan chain activation, and capture cycle width 1 to 0 determines the number of capture cycles. During fast capture, the OCC routes the fast clock through the fast clock CGC to clock out, bypassing the slow clock path. The OCC control block manages scan output and clock selection. In this mode, the kill clock enable signal can be used to block the fast clock from reaching clock out when not needed. This is particularly useful during functional operation or in the capture phase of shift-only mode. The diagram shows how clock paths are dynamically controlled based on test mode and shift-only mode settings. This diagram illustrates the Tessent On-Chip Clock Controller, on-chip clock, in kill clock mode, where the fast clock is disabled to prevent clocking during test operations. The kill clock enable signal activates this mode, which disables the fast clock CGC and forces the clock out to use only the slow clock via the slow clock CGC. The sync cell is bypassed when fast capture mode is active, allowing direct control of the scan chain by another on-chip clock upstream. This enables hierarchical test control across multiple on-chip clocks. The shift reg CGC controls the shift operation using either fast or slow clocks based on mode settings. In shift-only mode, the capture cycle width is ignored, and only shifting occurs. The scan-in and scan-out signals are routed through the shift reg block, with scan enable enabling the scan path. The on-chip clock control logic manages clock gating and scan enablement based on test mode and other inputs. This diagram illustrates the active upstream parent mode of the Tessent On-Chip Clock Controller, on-chip clock controller. In this mode, the on-chip clock controller bypasses the sync cell to allow a downstream on-chip clock controller to drive the fast clock signal directly from an upstream on-chip clock controller. This enables clock coordination across multiple on-chip clock controllers in a hierarchical scan chain. The active upstream parent on-chip clock controller input triggers the bypass logic, routing the scan-in signal through the shift register block without passing through the sync cell. The shift register clock gate control and fast clock gate control gates ensure that only the appropriate clock is enabled during shift and capture phases. During shift operations, the local slow clock is used for shifting data through the scan chain, while the fast clock is driven by the upstream on-chip clock controller. This mode supports efficient test pattern application in multi-clock domain designs where clock synchronization is critical. This timing diagram illustrates the slow speed capture mode in Tessent OCC, where scan enable is asserted to enable scan operations. During this phase, the slow clock drives both the shift register and the capture process. The shift reg clock signal follows the slow clock rhythm, ensuring synchronized shifting of condition bits. When scan enable is high, the clock out signal generates a series of pulses based on the condition bits loaded into the shift register. These pulses are derived from the slow clock, allowing for controlled capture cycles. The orange region highlights the active scan period during which capture occurs at a slower rate. The capture cycle width parameter determines how many slow clock cycles are generated per capture event. In this example, it's set to 10, enabling up to 3 sequential stages to be captured. This mode is useful for testing circuits with limited timing margins or when precise control over capture timing is needed. This timing diagram illustrates the fast capture mode operation in the Tessent On-Chip Clock Controller. When scan enable is asserted, the controller switches from slow clock to fast clock for capturing scan data. During the fast capture window, the sync cell Q signal transitions high, enabling the shift reg clock to follow the fast clock edge rate. This allows faster test data capture while maintaining synchronization with the scan chain. The clock out signal reflects the active clock source. It follows slow clock during normal operation and switches to fast clock during the capture phase as shown by the orange highlighted region. This diagram illustrates the Tessent On-Chip Clock Controller, on-chip clock, integrated with an IJT-AG interface. The on-chip clock manages clock signals during scan testing, enabling control over both fast and slow clock paths. Inputs such as scan enable, scan in, and various IJT-AG control signals are routed into the core on-chip clock control block. The on-chip clock features two clock gating cells, fast clock CGC and slow clock CGC. These are controlled by enable signals derived from the on-chip clock logic. The fast clock path is directly enabled via fast clock enable, while the slow clock path includes a multiplexer that selects between the external slow clock and the injected IJTAG TCK signal. When inject TCK is asserted, the MUX selects IJTAG TCK to drive the slow clock path through the slow clock CGC and output MUX, allowing test clock injection for boundary scan or embedded core testing. This enables precise timing control during a TPG-based scan tests. This diagram illustrates the Tessent On-Chip Clock Controller, on-chip clock, integrated with an IJT-AG interface, enabling test clock control during scan operations. The on-chip clock receives scan and IJT-AG control signals such as scan enable, scan in, and IJT-AG control enable through the on-chip clock control block, which manages test mode logic. The key feature shown is the clock multiplexing for the slow clock path. When inject TCK is asserted, the MUX selects IJT-AG TCK instead of the external slow clock, routing it through the slow clock CGC gate to drive clock out. This allows precise TCK injection during boundary scan testing. Fast clock paths are controlled independently by a fast clock CGC, gated by fast clock enable. Both clock paths converge at the output MUX, where clock MUX select determines which clock drives clock out. This architecture supports flexible clock management during a TPG and debug modes. This diagram illustrates the original clocking structure before DFT insertion. The functional clock signal, labeled clock, drives a series of sequential elements represented by yellow flip-flops. The clock signal is generated using the command add clocks clock pulse always, which creates a continuous clock pulse. This clock directly connects to multiple flip-flops in the design, forming the functional timing path. In this setup, the clock signal is intended to be reused as the test clock for DFT operations. However, without proper isolation, using this clock directly for test purposes can lead to DRC violations due to conflicting clock gating logic. This diagram illustrates an incorrect placement of the on-chip clock controller, on-chip clock controller, in a scan test environment. The on-chip clock controller is positioned directly on the functional clock path, which can interfere with the free-running clock signal to clock gating cells. The test clock and clock inputs feed into the on-chip clock controller, which then generates edit clock and shift capture clock signals. However, this placement disrupts the clean clock distribution needed for proper clock gating operation during normal mode. As shown, the resulting clock tree downstream receives these modified signals, potentially causing timing violations or unintended behavior in functional logic. This misplacement violates best practices for on-chip clock controller integration in hierarchical designs. This diagram illustrates the correct placement of an on-chip clock controller, in a scan test environment. The on-chip clock controller is positioned after a user-added buffer on the functional clock path, ensuring it does not interfere with the direct clock signal to clock gating cells. The test clock and EDT update signals are combined into a shift capture clock, which feeds into the on-chip clock controller. This setup allows the on-chip clock controller to control scan operations without disrupting normal functional clocking. The clock signal is routed through the on-chip clock controller and then distributed to multiple scan chains, shown as yellow blocks. By placing the on-chip clock controller after a buffer, write enable maintain timing integrity and avoid contention between test and functional modes. This diagram illustrates a core-level test clock architecture using Tessent On-Chip Clock Controllers, OCCs. The parent OCCs operate in parent mode and receive input from a PLL, generating control clock signals for child OCCs within the core. These child OCCs manage scan shift and capture operations for individual scan chains. The slow clock provides a reference timing source that feeds into both parent OCCs and directly to the EDT, embedded design test, logic. During test mode, the test clock is derived from the parent OCCs and distributed to the child OCCs, enabling synchronized control of scan cells across multiple clock domains. Each child OCC drives its own scan chain via green paths, ensuring proper timing during shift operations. This setup allows for independent clock control per scan chain while maintaining global synchronization through the parent hierarchy. Timing closure must account for both functional and test clock paths to meet shift timing requirements. This diagram illustrates the integration of a standard on-chip clock controller, on-chip clock, within a core for test mode operation. The phase-locked loop generates the primary functional clock, which is routed to both standard on-chip clock instances. These on-chip clocks manage clock distribution during scan operations. During shift mode, the test clock drives all scan cell clocks through the on-chip clocks, ensuring synchronized timing across the core. This eliminates clock skew between different branches and allows timing analysis to be closed without functional clock interference. The slow clock path feeds into the embedded design test block, which controls test clock generation. The red line labeled test clock represents the dedicated test clock signal that bypasses functional paths, enabling independent test timing. This setup simplifies hierarchical testing and avoids the need to balance functional and test clock paths. This diagram illustrates the Tessent On-Chip Clock Controller. On-Chip Clock Controller. Configuration when a capture-enable input is used. The on-chip clock controller manages clocking during scan operations, particularly enabling slow clock pulses during both shift and capture cycles. A key feature is the clock gator on the slow clock input, which is controlled by an OR gate combining scan, enable, and capture enable signals. The synchronization cell ensures proper synchronization of the scan enable signal, while the shift register clock gator controls the fast clock path for shift operations. During test mode, the system can operate in fast capture mode or shift-only mode, allowing flexible clock control. The fast clock gator and slow clock gator gates manage the respective clock paths based on mode selection. The output clock out is selected via a multiplexer that chooses between fast clock and slow clock based on the clock multiplexer select signal. This architecture supports both free-running and tester-driven slow clocks, providing flexibility in test environments. The bypass shift flip-flop register allows skipping the shift register path under certain conditions. This diagram illustrates key clock signal parameters used in Tessent's on-chip clock controller for test pattern generation. The horizontal line represents the test clock waveform, with annotations defining critical timing attributes. The test clock period defines the full duration of one complete clock cycle, measured from rising edge to the next rising edge. This value is typically set in the do file and determines the base timing for scan operations. The test clock pulse width % specifies the duty cycle of the clock pulse, indicating how long the high phase lasts relative to the total period. For example, a 25% width means the high level lasts 1/4 of the period. The test clock rise % indicates the point within the clock period where the rising edge occurs. Combined with the pulse width, this helps define the precise timing of capture and shift phases during scan testing. This waveform illustrates the clock behavior during a fast capture operation in Tessent's on-chip clock controller, on-chip clock. The green lines represent clock signals, showing how the capture clock is synchronized with scan operations. The red arrows highlight the timing of the capture event. The first arrow points to the rising edge that triggers the capture of test data into flip-flops. This occurs immediately after the serial load phase, ensuring minimal latency. The second arrow indicates the subsequent capture cycle, demonstrating the on-chip clock's ability to perform multiple captures efficiently. This sequence enables high-speed testing without requiring complex external timing control. This waveform diagram illustrates the timing relationship between the scan clock and capture clock during a fast capture operation in Tessent's on-chip clock controller, on-chip clock. The green lines represent the clock signals, with the top signal being the scan clock and the bottom one the capture clock. The red arrows highlight the critical timing phase where the capture clock transitions high after the scan clock has stabilized. This ensures that data is captured reliably into the flip-flops without violating setup or hold times. Fast capture mode allows for efficient test pattern application by overlapping scan, shift, and capture phases. In this mode, the on-chip clock automatically configures clock restrictions and input constraints to maintain timing integrity. The diagram shows how the capture event occurs shortly after the scan data is latched, enabling high-speed testing while preserving signal stability. The standard on-chip clock controller, on-chip clock, manages clock signals for scan testing. It receives a reference clock and a slow clock as inputs, with the reference clock feeding into a phase-locked loop, to generate a fast clock. The fast clock is used for high-speed capture operations, while the slow clock supports shift operations and slower capture modes. Both clocks are routed into the standard on-chip clock block, which performs clock selection, chopping control, and gating. Inside the on-chip clock, a scan programmable shift register allows a TPG tools to dynamically suppress or pulse clock cycles during test application. This enables flexible timing control essential for pattern retargeting in test mode. This diagram illustrates the logic structure of the standard on-chip clock controller, on-chip clock, used in Tessent design for test. The on-chip clock manages clock signals during scan operations, providing both fast and slow clocks for capture and shift phases. Key inputs include scan enable, test mode, and capture cycle width 1 to 0, which control the behavior of the clock selection and gating. The core of the on-chip clock is the shift register block, which receives scan in and generates scan out based on the capture cycle width. This register enables a TPG to suppress or pulse clock cycles as needed. The sync cell ensures timing alignment between scan chains and clock domains. Clock selection is controlled by the clock mux select signal, derived from test mode and shift-only mode. The fast clock CGC and slow clock CGC blocks gate the respective clocks using enable signals from the on-chip clock control logic. The final clock out is selected dynamically based on the current test mode, supporting both fast capture and normal shift operations. This diagram illustrates the parent OCC operating in standard mode, where it performs clock selection only. The reference clock and slow clock inputs are fed into a PLL, which generates the required clock signals. These clocks are then selected by the parent OCC based on test mode requirements. The parent OCC forwards the selected clock to a downstream child OCC, which handles clock gating and chopping. This separation allows for precise control over clock distribution during testing. The child OCC is connected to both core boundary logic and top-level logic, enabling targeted testing of boundary scan chains and internal logic. In this configuration, the parent OCC does not perform clock gating. This responsibility is delegated to the child OCC. This setup is commonly used in EX test or IN test modes for pattern retargeting, where interactions between core-level wrapper chains and top-level logic need to be tested without interference from clock gating. This diagram illustrates the parent mode operation of a Tessent On-Chip Clock Controller, On-Chip Clock Controller. In this mode, the parent on-chip clock controller performs only clock selection and bypasses its internal clock gating logic. It receives inputs from both a reference clock and a slow clock, which are processed through a phase-locked loop to generate the desired clock signal. The selected clock is then passed downstream to one or more child on-chip clock controllers operating in child mode. These child on-chip clock controllers handle the actual clock gating and chopping functions, enabling fine-grained control over clock distribution to specific scan chains or logic blocks. This architecture is commonly used during external test or internal test modes for pattern retargeting, where interactions between core-level wrapper chains and top-level logic need to be tested. The separation of clock selection, parent, and gating, child, allows flexible and scalable test clock management. This diagram illustrates the parent mode on-chip clock controller, logic, which manages clock distribution during scan testing. In parent mode, the on-chip clock controller selects and gates clocks for top-level test operations without requiring shift clock routing to child modes. The shift clock is injected at the base of the clock tree, simplifying hierarchical test control. The core functionality revolves around the shift register block, which captures scan-enabled signals and controls clock pulse generation based on capture cycle width. When scan enable is low, a programmable number of clock pulses are passed through, enabling precise timing control. The sync cell ensures proper synchronization between scan inputs and internal logic. Clock outputs are derived from fast clock CGC and slow clock CGC blocks, which select between fast and slow clocks based on test mode and shift-only mode inputs. The final clock out signal is multiplexed using clock mux select, allowing dynamic clock selection during test sequences. This architecture supports efficient hierarchical scan testing with minimal overhead. This diagram illustrates the clock control flow in a child mode on-chip clock controller. On-chip clock architecture. A reference clock and a slow clock feed into a phase-locked loop, which generates a stable high-frequency clock signal. The phase-locked loop output is then fed into a parent on-chip clock operating in parent mode, which acts as the master controller for downstream clocks. The parent on-chip clock distributes the clock to multiple child on-chip clocks, each capable of independently gating or chopping the clock based on scan programmable settings. Each child on-chip clock receives the clock from the parent on-chip clock and applies optional internal clock gating using a programmable enable signal. This allows precise control over clock distribution during test modes, enabling power savings and improved testability. The structure supports hierarchical clock control, essential for complex SoC designs. This diagram illustrates the child mode operation of the Tessent On-Chip Clock Controller, on-chip clock. In this mode, the on-chip clock receives control signals from a parent on-chip clock and generates clock enable signals based on scan programmable settings. The Shift Reg module captures test configuration data via scan-in and scan-enable, storing values for capture cycle width 1 to 0 that define how many clock cycles are enabled during scan operations. These values are used to generate a clock enable signal through logic gates. The bypass path allows direct propagation of scan-out when test mode is active, bypassing the shift register. The final clock out is derived by gating the input clock with the generated clock enable signal, enabling precise clock chopping for test purposes. This diagram illustrates the hierarchical structure of Tessent On-Chip Clock Controllers, OCs, showing a parent OCC in parent mode connected to multiple child OCs. The parent OCC receives input from both a reference clock and a slow clock, which are processed through a PLL before being distributed. The parent OCC generates clock signals that are passed down to child OCs operating in child mode. Each child OCC has an enable signal and a clock output, allowing for independent control of downstream clock domains. This setup supports flexible clock gating during test mode. Critical for DFT operations, the enable signal from each child OCC must have a sensitized path to any associated clock gators to ensure proper controllability during capture. The tool verifies this connectivity. If not met, the clock gator is disabled during testing. This diagram illustrates the child mode on-chip clock controller, on-chip clock. Logic without a clock gator. It shows how scan and test signals are routed through shift registers and control logic to manage clock enable outputs during scan operations. The core of this design is the shift register block, which receives scan in, scan enable, and capture cycle with 1 to 0 inputs. This register controls the timing of clock enable pulses during capture cycles, allowing precise control over when clocks are enabled for testing. The bypass path via bypass shift FF reg allows direct routing of test mode signal to the scan-out reg, enabling test mode bypass functionality. The final output, clock enable out, is generated by combining the shifted control signals with the test mode input, ensuring proper clock gating behavior during scan tests. This timing diagram illustrates how the Tessent On-Chip Clock Controller, on-chip clock, manages fast clocks during scan capture mode. When scan enable transitions from 1 to 0, the on-chip clock enters capture mode, triggering a sequence of synchronized events across multiple clock domains. The slow clock edge at point 1 synchronizes the scan enableable transition. This is followed by 2 fast clock 1 pulses, 2, which ensure proper alignment before the third pulse, 3, triggers the actual capture phase. The clock-out signals are generated based on this timing, with clock-out 1 showing a single pulse aligned to the third fast clock 1 edge. Note that while all 3 fast clocks are synchronous in function, their capture phases start at different times due to variations in scan enable and slow clock arrival across on-chip clocks. As a result, clock-out 1, clock-out 2, and clock-out 3 are not synchronized with each other, enabling independent at-speed testing of functional paths. This waveform diagram illustrates how the synchronous on-chip clock controller, Sync OCC, aligns clock edges during scan capture mode. The orange region represents the active capture window, triggered by fast capture mode and scan enable signals. During this period, slow clock drives the system, while multiple fast clocks, fast clock 1, fast clock 2, fast clock 3, are synchronized to ensure proper timing for test data capture. The Sync OCC generates aligned output clocks, clock out 1, clock out 2, clock out 3, based on 2 different configurations. In configuration 1, the outputs are aligned such that clock out 2 and clock out 3 fire at specific phases relative to each other, enabling testing of short paths like between fast clock 2 test enable and fast clock 3 LE. Configuration 2 shows an alternative alignment demonstrating flexibility in edge placement. By using a single synchronous OCC, avoid the complexity of managing multiple independent OCCs. This ensures consistent and predictable clock edge alignment across synchronous divided clocks, which is critical for accurately testing shortest timing paths in the design. This diagram illustrates how the pulse-to-align register controls clock pulse alignment in the synchronous on-chip clock controller. On-chip clock controller. The two waveforms represent outputs of synchronous clocks under different pulse-to-align settings 00 and 01. When pulse-to-align is set to 00, all clock pulses are aligned to the rising edge at index 0 of the slowest clock. This ensures that capture events occur simultaneously across all clock domains. When pulse-to-align is set to 01, the alignment shifts to the rising edge at index 1 of the slowest clock. This allows testing scenarios where capture timing needs to be offset by one cycle. The horizontal axis shows time in clock cycles, with indices 0 through 7 marking key edges. The pulse-to-align register is a 2-bit shift register that determines which edge of the slowest clock all other synchronous clocks align to. Since only 2 capture pulses are shown here, only values 0 and 1 are valid. In general, the maximum alignment index is limited by the capture cycle width property, which defines how many capture pulses are used per pattern. This diagram illustrates the synchronous on-chip clock controller, on-chip clock, used in Tessent design for test solutions. It manages multiple clock domains during scan testing, enabling precise control over fast and slow clocks. The U-tag block receives J-tag inputs like scan enable and test mode to configure the scan chain operation. The on-chip clock uses shift registers, 3 4-bit and 1 2-bit, to store configuration data from the J-tag interface. These registers control clock enable signals for different clock frequencies, fast clock F1, F2, and F4, as well as the slow clock. The cap cycle config 1 to 0 determines the capture cycle behavior. Clock multiplexing is achieved through a series of AND gates and multiplexers driven by the clock mux select signal. This allows selection between fast and slow clock paths based on test mode requirements. The logic ensures that only the appropriate clock is enabled during each phase of the scan operation. This diagram illustrates the control logic for the synchronous on-chip clock controller, Sync OCC, which manages multiple clock frequencies during scan operations. The architecture is divided into 3 distinct control circuits, 1 for the slowest frequency and 2 for faster frequencies, each handling a specific clock domain. Each control circuit receives scan inputs and mode bits to determine when to enable clock pulses. The scan in signals are routed through individual control blocks that generate scan out and CLK enable signals based on the current scan phase and configuration. The pulse-to-align signal from the SyncGen module helps synchronize the capture phase across different clock domains. The bottom-level control circuit for the fastest clock, fast clock F1, uses cap pulse config 1 to 0 to configure its behavior, ensuring proper alignment of capture pulses. This hierarchical design allows precise control over clock enabling in multi-clock environments, critical for reliable scan testing. This diagram illustrates the control logic for the faster clock frequencies in the synchronous on-chip clock controller, Sync OCC. The design uses a 4-bit shift register to manage scan mode operations, with inputs from scan in and control signals like test mode and fast cap mode. The 2-bit counter starts incrementing during the capture phase and saturates when it reaches the value specified by the pulse-to-align 1 to 0 bus. Once saturated, it enables the faster clock pulses via the shift register output. Key outputs include CLK enable, clock mux select, and scan data 3 to 0, which coordinate clock gating and scan chain behavior. The slow clock and fast clock signals are controlled through multiplexing based on scan mode and configuration settings. This diagram illustrates the control logic for the synchronous on-chip clock controller, Sync OCC. The core function is to manage clock enable signals during scan operations, particularly aligning fast clocks with capture phases. Inputs such as sync in, scan enable, and cap pulse config determine when the system enters scan mode and how capture pulses are generated. The 4-bit shift register plays a key role in synchronizing the fast clock pulses. It starts incrementing during the capture phase and saturates at a value defined by the pulse-to-align 1 to 0 signal. This ensures precise timing alignment between the slow and fast clocks. Once the shift register reaches the target count, it enables the fast clock via the SyncGen module. The output sync out is then driven based on the state of the shift register and other control signals like fast cap mode and test mode. This mechanism allows accurate clock gating and pulse generation during a TPG testing. This diagram illustrates the Tessent Synchronous On-Chip Clock Controller, Sync OCC, configuration when managing multiple clocks of the same frequency. A single 4-bit shift register is used to generate clock-enable signals for all fast clocks operating at identical frequencies, such as fast clock 0, fast clock 1, and fast clock 2. The scan-in and scan-enable signals control the loading of test patterns into the 4-bit shift register via the JTAG interface. The output of this register drives a multiplexer that selects between slow clock and fast CLK enable based on test mode settings. This shared control ensures synchronized behavior across all same frequency, fast clocks. Because only one shift register is used, individual phase delays cannot be applied to each fast clock. Instead, all clocks of the same frequency are aligned together. When edge alignment is requested with respect to the slowest clock, all synchronous clocks of the same frequency will align accordingly, maintaining consistency in timing during test operations. This diagram illustrates the Synchronous On-Chip Clock Controller, On-Chip Clock Controller, with a bypass shift register. The On-Chip Clock Controller manages multiple clock domains, including slow clock and several fast clocks, fast 4-1, fast 2-1, etc., enabling flexible test mode control. The bypass shift register allows scan chains to remain functional even when the on-chip clock controller is inactive. This is critical during test operations where other parts of the design are under test, ensuring continuous scan shifting through the scan-in and scan-out ports. Signals like I, JTAG, XOX, test mode, and cap cycle config 1 to 0 configure the on-chip clock controller behavior. The 4-bit and 2-bit shift registers handle control logic, while the flip-flops and multiplexers route clock signals based on test conditions, supporting both normal operation and LBIST modes. This diagram illustrates the bypass shift register within the Tessent On-Chip Clock Controller, OCC, used during scan test mode. The core consists of a 4-bit and a 2-bit shift register, controlled by scan-enable sync and test mode signals. These registers manage clock control logic during test operations, particularly for aligning pulses and enabling clock multiplexing. The bypass clock signal is derived from the fast clock input when test mode is active, allowing the system to bypass normal clock paths. The scan-in data flows through the 4-bit shift register, with its output feeding into the 2-bit register, which then drives sync out and pulse to align 1 to 0. This enables precise timing alignment during scan capture. Key control signals like scan enable, slow clock, and fast capture mode are synchronized via flip-flops to ensure proper timing across clock domains. The final outputs include clock mux select, slow CLK enable, and scan data 3 to 0, which are used to configure clock routing and scan chain behavior during a TPG testing. This diagram illustrates the integration of a synchronous on-chip clock controller, Sync OCC, within a clock distribution network. The reference clock and slow clock inputs feed into a phase-locked loop, PLL, which generates higher frequency clock signals. The PLL output is then divided by factors of 1/2 and 1/4 to produce multiple clock frequencies. These divided clocks are routed to the Sync OCC, which acts as a central control point for managing clock domains during test modes. The Sync OCC enables precise synchronization between different clock domains, particularly important in hierarchical ATPG scenarios. It allows controlled clocking during scan operations, ensuring proper timing alignment across logic blocks. This diagram illustrates the flat ATPG scenario using a synchronous on-chip clock controller, Synchronous On-Chip Clock Controller. The reference clock and slow clock inputs feed into a PLL, which generates multiple clock frequencies. These are then divided by factors of 1/2 and 1/4 before being routed to the Synchronous On-Chip Clock Controller. The Synchronous On-Chip Clock Controller manages clock distribution across domains A and B, ensuring proper synchronization during test mode. The arrows indicate clock signal flow and interaction between domains. In this setup, the Synchronous On-Chip Clock Controller is placed at the root of the clock source, enabling unified control over clocking for a TPG. During a TPG, the Synchronous On-Chip Clock Controller allows independent control of clock domains while maintaining timing integrity. This enables efficient scan testing without requiring complex external clock control logic. This diagram illustrates a hierarchical ATPG setup using Tessent Sync OCC in a multi-core design. A reference clock enters a PLL, which generates a slow clock used to drive two sync OCC instances, one at core B and another inside wrapped core A. The sync OCC at core B divides the clock by 1/2 or 1/4 before passing it downstream. This allows independent clock control for test purposes. The sync OCC in core A is inserted at the clock source point within the core, enabling isolated testing. During a TPG, only one OCC can be active at a time. When testing core A in internal test mode, the OCC in core B is disabled. Conversely, when testing core B with core A in external test mode, the OCC in core A is disabled. This prevents conflicts in clock domain control. This diagram illustrates the synchronous on-chip clock controller, on-chip clock, used in Tessent design for test flows. The on-chip clock manages multiple clock domains during test mode, allowing precise control over scan and capture operations. Inputs such as scan-in, scan-enable, and JTAG signals configure the controller's behavior. The on-chip clock receives various clock inputs, slow clock and multiple fast clocks, F41, F21, etc. These are routed through multiplexers controlled by internal shift registers and configuration signals like cap cycle config 1 to 0 and fast capture mode. The 4-bit and 2-bit shift registers store test mode settings from JTAG. Clock selection is dynamically managed via a hierarchical mux chain. The clock mux select signal determines which fast clock is passed to the scan logic. This enables flexible clock switching during a TPG test patterns, supporting both high-speed capture and low-speed scan operations. This DFT specification defines a synchronous on-chip clock controller, OCC, with multiple clock domains. The controller block specifies clock intercept nodes for different frequency ratios, enabling precise control over clock signals during test mode. The frequency ratio 2 and frequency ratio 4 blocks define how clocks are scaled and intercepted. For example, fast clock F11 node and fast clock F12 node are intercepted at a ratio of 2, while fast clock F41 node is used at a ratio of 4. Connections specify the source clocks. Fast clock 2 source drives the ratio 2 domain, and fast clock 41 source drives the ratio 4 domain. Note that fast clock is connected to no source in one case, indicating it may be derived or disabled. This DFT specification defines a synchronous on-chip clock controller, on-chip clock, with multiple clock domains. The on-chip clock is configured with 2 clock ports, each supporting different frequency ratios. The first frequency ratio 2 block specifies a clock domain with a 2-to-1 ratio and 2 clock ports. This allows the controller to manage clocks that run at half the speed of the base clock. The second frequency ratio 4 block defines another domain with a 4-to-1 ratio but only 1 clock port. This configuration supports slower clocks derived from the main clock source, enabling mixed clock test scenarios. The sync OCC requires all lower divided clocks as inputs when a higher division is used. For example, if a design uses a 1/8 clock, the sync OCC must receive both 1/2 and 1/4 clocks as inputs, even if they are not used in the design. In the supported configuration, the PLL generates fast clock div 2, and fast clock div 4, which are all fed into the sync OCC. This ensures proper synchronization and timing alignment. The unsupported configuration shows only fast clock being provided to the sync OCC, with 1/2 and 1/4 clocks generated downstream. This violates the requirement that all dividers must feed into the OCC, not after it.